Okay, welcome back. So this class we will finish 3 exercises. But before we do the 3 exercises, I would like to go quick summarize. As the previous class, we say that we have a Nano's transport theory. Okay, and the Nano transport theory tells us the B is extensive properties change with the time. Okay, but this is dB dt is in the closed systems, and then is equal to the dB dt in the CV. In the CV is a control volumes plus the B rate, but this is the outflow, minus the B rate, but this is the inflow. And we know that the B rate outflow minus B rate inflow is equal to the B rate net. Okay, so we can rewrite the equations. This is the BCV, the B in control volume change with the time plus the B rate net. This is the net outflow rate. Okay, and then we know that the BCV, the extensive property in the control volume, if you use the integration operators and integrate along the CV space. And you know that is the small b is intensive properties multiply the rho is the density and the small volume changes. And the final is the B rate net, can also represented by the integration operators, but we change the integration operator that integrates along the control surface. And we still have the B, and we also have the density. But the difference in here, we multiply the velocity factors with the cross-section area factors. So the difference is there is the product operators. Okay, and you see the velocity multiplied the cross-section area is the discharge. And discharge multiplied the rho, and the B is equal to the B rate net. Okay, so we can rewrite the equation by here is the control volumes B rho D V plus integrate along the control surface B rho, but there is the factor operators from dot product to the cross-section area dA. And then we know that the B is divided by the capital B divided the mass. And then in here, in this chapter, we always focus on the mass problems. So that means usually we use the B is equal to 1, and then the capital B is equal to the mass. So there is the Reynolds transport series, and we use the mass and replace the capital B by the mass. So we can rewrite the Reynolds transport theory to become the dm dt, and also this is in the closed systems is equal to the dm cv and dt. Okay, and the plus there is the B rate net, so this is the mass rate net. And we can also rewrite the equation by the integration problems. So we integrate, this is a d and the dt. Sorry, there is the bcv. So we still need to edit additional d and dt in here. Okay, so there is a d and dt, and the inside is integrate along the control volumes, no dv. Because now we are focused on the problem related to the mass, so the b is here is equal to 1. And the following integrate along the control surface, and this b is equal 1, so we only have a rho v dot product with the cross-section area vector. Okay, so as I mentioned, we convert the Reynolds transport to the continuity equation. But how can we convert from the Nano transport equation to the continuity equations? We assume the mass is follow the conservations. The mass is always constant. Okay, that means the dm dt in the closed systems is always equal to 0 because the mass didn't change with the time in the closed system. So we can rewrite the Nano transport equations by the continuity equations. Okay, so we don't have the items in the left hand side. So we know that the d and dt, the mass in the control volumes, plus the cs, rho, v, and dA is always equal to 0. And if we don't use the integration operator to represent the continuity equation, we can rewrite the continuity equation by the dt dmcv plus the sigmas for the m rate out minus the sigma m rate in equal to 0. So This is our two formulas represented for the continuity equations. And this is the original formulas, this general formulas for the Nero's transport theory. Okay, so now we move to the exercise. We see the problem. This is the first exercise, and as you see, the exercise is just required to apply the continuity equation to a tank with only an inflow and outflow. So we see the questions. We have the incoming water, the flow velocity is 7. So we have a flow velocity is 7 meter per second. This is for the inflow, and the cross-section area is the 0.0025 meters square. Since we know if we have the velocity and we have the cross-section area, we can compute the discharge, right? So this is for the inflow. We use the label 1, and we have the discharge 1. So it's equal to the V1A1. And you can use your calculator to compute the discharge 1. Okay, it's the 7 multiplied 0.0025. So discharge is equal to 0.0175 cubic meter per second. Okay, and we can keep to see the questions. Water also flow out the tank. So we have a flow out the tank at a rate. The Q is 0.003. So we know the flow out. We use the label 2. And we already have the discharge number 0.003 cubic meter per second. And the question tells you the water density is equal to 1,000 kilograms per meter cubic. Okay, and what is the rate at which water is being stored or removed from the tank? So for these questions, we define the control surface. This is our control surface, and inside the control surface is our control volumes. Okay, but for all systems, the mass didn't disappear. So that's why we apply the continuity equation for these problems. So following the continuity equations, we know that the MCV change with the time is plus the total flow out. This is the flow out rate minus the total inflow rate, and it will equal to 0. Okay, so the questions we need to answer the rate of the water is being stored or removed. So this is indicate these items related to these items. And now we already know the outflow and the inflow because we know the discharge 1 and discharge 2. So we can compute the outflow and the inflow, the net of the outflow rate. Okay, so first we compute we only have one outflow is related to Q2. So this is the outflow rate is equal to the rho Q2. Okay, so we know the Q2 is 0.003 and the density is 1000. Okay, so this is equal to the 3 kilograms per second. And what is the inflow? This is the inflow rate is equal to the rho Q1. Rho Q1. And the Q1 is 0.0175 and the multiplier density 1000. So is equal to 17.5 the kilograms per second. So we make the balance, we put the two numbers, go back to these continuity equations. So we have d and cv dt plus 3 kilogram per second minus 17.5 kilogram per second is equal to 0. So finally we know that the d and cv dt is equal to the 14.5 kilogram per second. Okay, so we know that after the inflow and the outflow balance, we know the mass in the control volumes will increase because the number showing here is the positive. So we can conclude that the water is being stored. Okay, but the sentence notice that the rising level of the water in the tank causes air to flow out of the CV. But in this problem, we didn't care the air flow out from the CV because the air of the density is quite smaller compared to the water. So for this problem, even though we actually know the air will flow out, but we didn't take into account in our computings. It's the reason showing here because the air of the density, the air is quite smaller. Okay, so this is very basic questions. If we take a look one tank and we have some inflow and we have the outflow and we just want to know the water in the tank is decrease or increase. So it's related to the D and CVDT values. And for this problem, this is the positive. So we know that water is being stored. Okay. So the next, this is another exercise. Also, the question requires we apply the continuity equation to calculate the rate of the water rise in the reservoir. So the question directly tells you the water is rising. So what is the rate of the rise of the water in the reservoir? Okay, so again, we know the river discharge is to be the inflow of these reservoirs. So we have the Q1, this is the inflow discharge, is the 400 and 1000 in here. And we see that the unit is the CFS. CFS. So what is the CFS? We know that the CFS is the unit, dimensional unit for the discharge. So I tell you the CFS is equal to the FT cubic per second. Similar, if we call that is the CMS, so that means the unit is the cubic meter per second. Okay, so in our questions we use the CFS, so that the unit in here is the FT cubic per second. Okay, and then we see the questions. We also know the outflow rate for this problem. The Q2 is outflow rate for this problem. Okay, is 250 and 000 FT cubic per second. And we also know that the reservoir surface area, we use this is the A3 labels, is the 40 mile square. And we know that the 1 mile is equal to 5280 FT. So we need to convert the unit to FT square. So the 40 multiply the 5280 square, and we change the unit to the FT square. Okay, and the questions we need to answer: what is the rate of the rising waters? So the rate of the rising water is V3. So we need to answer how large of the V3 numbers. So we go back to see the problems. We already depict the control service. The dash line is our control service, and the inside control service line, we call that is the control volumes. And we already tell you the water is rising, so the mass, the MCV mass in the control volume during this problem cannot be changed, because the water is rising up rising, so the mass in the dash line, inside the dash line, didn't change for this problem. So if we base on the continuity equation showing here, that means we don't have these items, because the mass in the control volume is always constant. So for these questions, we only need to process the mass outflow along the control surface minus the mass inflow along the control surface is equal to 0. So we just make the balance. How many outflow we have? We have the 1 and the 2. They are the outflow. So for the outflow, we have the Q2 multiply the row density, okay, and plus the A3 plus the A3 multiply the flow 3. The flow 3 is our rising rate, and the multiplier row, this is the two items related to the outflow, and the minus the inflow. We only have the one inflow Q1, so this is the Q1 multiply the row, and the finally is equal to 0. Okay, so we make the balance. So we know that the A3 V3, and we cancel out all the row, the free densities, and it's equal to the Q1 minus the Q2, and the V3 is equal to Q1 minus Q2 divided the V3, right? Oh, sorry, not the V3, divided the A area 3. So this is R is the 4,0,0,0,0 minus the 2,5,0,0,0, and the divided what? Divided 40, divided 40, and the later is the convert from 1 mile to the FT. Okay, so 5280 square, and you can use your calculator to compute the V3. So 4,0,0,0,0 minus 250,000 divided the 40, and divided the 5280 square, 5280. Okay, so the answer in here is 1.34, and the 10 minus 4 powers, and the unit in here is the FT divided the seconds. And usually for these problems, the unit for time we will convert to the hours. So for this problem, we change the second to the hours. We need to multiply the 3600 to convert the second to the hours. Okay, so the final answer in here is 0.484 FT divided per hour. Okay, so a little bit change difference compared to the answer right down in here, but this is the basic idea. When we take a look for the problem, we need to define what is our control surface. The control surface is our boundary for the control volumes. Since we define the control volume already, and we look our questions, we know the condition is the water always increase. If the water always increase, so the mass inside the dashed line will not changes when the time changes. So we always satisfy that the NCVTT is equal to 0. So we only need to process the net mass flow for this problem. And this problem, we have the 2 outflow and only 1 inflow, and then make the balance so we know the rising water, the rate of the rising waters. Okay, so move to the final exercise today in this class. So again, this exercise also requires we apply continuity equation to predict the time for a tank. Okay, so what is the predict the time? So we take a look. The question tells us the jet of the water in here. The diameter is 10 centimeter, so it's equal to 0.1 meter. And the diameter for the tank here is the 1 meter. Okay, and the questions tell us the conditions is satisfy assumption that Bernoulli equations applies, and then the velocity in the jet is the root of the 2gh. So what are the meanings? The meanings, this is the dash line, is the string line, is our string line. As you remember, if along the string line, and we know that the V1 in here and the P1 in here, and there is the V2, P2, and along the same string line, so we can, based on the Bernoulli equation, the Bernoulli equation tells us the 2 over 1 low V1 square plus gamma Z1. The D1 is the height in here, and the plus the P1 is equal to 2 over 1 low V2 square plus gamma D2 plus P2. Okay, and we assume the V1 velocity is quite smaller than the V2. So this problem we ignore the V1 items. Okay, and the P1, P2 layer is exposed on the air environment. So the gauge pressure is also equal to 0. So we just balance the equations. We know that the 2 over 1 low V2 square is equal to the gamma Z1 minus Z2. Okay, V1 minus Z2. And we know in this problem, Z1 minus Z2 is equal to H. Okay, the water depth H, and the gamma is equal to the rho g. So we rewrite the gamma h to the rho gh. So we can cancel out the density, and finally we know that the V2 is the root of the 2gh. Okay, that's why the answer, the question directly tell you the velocity can be represented by this formula. Okay, so don't forget the Bernoulli equations ideas. This is focus related to our chapter 4. And then we see that the question tells us we need to answer is how long will it take for the water surface in the tank to drop from the H0 2 meters. So we have H0 is 2 meters, and the drop to the H final is 0.5 meter. So how long it is? So that's why this question is for the prediction of the time for the tank. Okay, so again we analyze if we can define our control volumes boundary for the control surface. So we can assume the boundary of the tank is our control surface. So for this problem, we only have the one flow. We have the flow out, and we don't have any flow in. And so based on the continuity equation, we know that the dmCv dt, and for this problem, we only have the flow out. So we have the flow out, the mass rate for the outflow, and then the answer is the balance is equal to 0. So what is the mCv for this problem? We know that we have the diameter here. The tank diameter is 1 meters. So we have the diameters. So we know the area is 4 pi d squared. And we know h value in here. So multiply the h. So this is the total volumes in the waters. Then the total volume in the water in a tank, we multiply the density. So this is the mass in the control volumes. Okay. And what is the M rate out? What is the M rate out? We know there is, we know the jet, the diameter of the jet is 0.1 meter. So we know the cross-section area of the jet is 4 over pi small d squared, and the flow out velocity is the root 2gh. So this is the area multiply the velocity. There is the discharge, and the discharge multiply the rho, and then this is the outflow mass rate. Okay, so we put the two equations result back to the continuity equation in here. So we know that the t 4 over pi d squared h multiply rho is plus 4 over pi d squared and the root 2gh, and the rho is equal 0, right? And then we take a look, we just cancel out the rho and the constant value 4 over pi, and we just reorganize the equations. So, and the d squared is not changed with the time. So I take out the d squared, and the inside we only have a d h dt. And I move this item to the right hand side. So the right hand side is minus d squared and the root 2gh. Okay, so and I just put the same parameter h to the left hand side here. So here we have the d h, and I take the root h under here, root h under here, and I move the dt to the right hand side, and the d squared also move to the right hand side. So the right hand side is minus d squared divided capital D squared, and we still have a constant value 2g and the dt in here. And we process this problem with the integration operators, and there some parameters are not related to the time. So the integration operator I can put here, and we know that the depth is from the 2 meters decrease to the 0.5 meters, and the time is the initial is 0, and there is our final times. So we do the integrations of these problems. We know that is the 2. We do the integration, so the left hand side in here is 2 times root h, and the integral interval is from 2 to 0.5. Okay, and it's equal to the minus d, small d is 0.1 squared divided, this is a capital D is 1 meter here, and the 2g root, so it's a 2g is 9.81, and we do the integration, so this is only have a t parameters. Okay, so based on this equation, you can solve how long of the water surface water decrease from the 2 meter to 0.5 meters. Okay, so I just put a number inside. So this is 2 multiply the root 0.5 minus the root 2. Okay, and the right hand side, you use your calculators. This is the minus, and this is a 0.1 square. 0.1 multiply 0.1. The multiply the 2 times G 9.81. Okay, so the right hand side is equal to 0.044 T, and you make the balance. Finally, you know the T is equal to around 31.9 seconds. Okay, so this is also a simple problems, but compared to previous two exercises, this problem, the boundary of the control volume will be changed because we fix the control volume with the water boundaries. And we know this problem, the water surface will decrease. So the boundary of the control volume will also change it. Okay. And you just apply the continuity equation and make the balance. So finally you can solve the T problems. So this is our final exercise today. And for the next class, I will keep going for different problems, but the problem also based on the continuity equations. Okay, so today I will also have some highlights for our quiz in next Monday. Okay, so I use the Chinese to interpret how kind of the quiz type we will have in next Monday. 所以下周我们礼拜一还是会上课，然后也是会及时上传这个上课的影片。那希望大家就在9点的时候可以准时收看我们 YouTube 的这个线上教材。那到时候会公布考试的题目在线上教材的影片当中。那主要我们下周一只会考第5个章节前面上课这些内容，那一定会考有关于这种 discharge 或是这种质量流率、这种 mass flow rate 的计算的一些相关问题。那第2个一定也会考的是今天线上这些教材就是我们有关于这个 Nano transport 这个理论，那后来衍生出这个 continuity equation 这部分，这种连续方程要怎么样用在这种流体或者是水体有在流动的时候，在一定的空间里面的质量是累积的还是减少的，或者是像刚才这些exercise， 他们可能会变相的去问你说，如果水是在下降，请问它花了多少时间下降到 0.5 meter， 或者是水其实在水库的水其实在蓄水，那请问它蓄水让水量抬升的速率有多快？所以会有一些这种题目的变形，但是其实都是仰赖我们这里教的这个连续方程。那可能问你这个速率可能有多快，或者是问你花了多少时间才可以从水深2米降到水深 0.5 米。OK， 那助教也有公告，就是相关的考试的这个线上缴交的方式。那我们会在13的平台开放作业缴交，那作业缴交会有截止的时间，那请大家就在截止的时间以前上传你的作答的这个过程，那以图档的方式上传。那13平台这个缴交作业系统其实上传有一个时间限制，超过那个时间就没有办法再上传你的解答，所以请同学务必要 在期限以前赶快上传你的作答的这个过程以及解答的这个最后的答案。那因为上传的是图档，所以我们没办法把每个图印下来，提供给同学作为这个改完考卷后的这个过程。所以如果你最后助教会在公告每一个人每次小考的成绩啊，如果你对于这个成绩有点问题，那你可以到这个助教的这个研究生室，然后去跟助教询问说相关的这些问题。那我们因为疫情的关系，所以目前暂时以这样的方式在做考试跟教学。那后续其实还是可以进行相关的这个修正或讨论。好，那今天就上到这里。